You're welcome to another introductory chemistry class, organic section, FSC 112. In today's class, we'll be looking at alkanes. At the end of this class, you understand what alkanes are, geometric isomerism in alkanes, the relative stabilities of these alkanes, their method of preparation, and their properties and reactions. Alkanes are generally referred to as olefins. They are organic compounds or they are hydrocarbons that contains carbon-carbon double bond. There are three types of alkanes. We have terminal alkanes. These alkanes have the double bond at the terminal carbon. We have internal alkanes. These alkanes have their double bond in the middle of the compound. We have cycloalkanes. These alkanes have their double bond in a ring form. Alkanes contain double bond, which is made up of pi bond and sigma bond. This double bond is sp2 hybridized, having trigonal planar shape and bond angle of 120 degrees. From the bond dissociation energy of alkane and alkane, it is observed that the pi bond of alkane is a weaker bond than sigma bond in alkane. Because of the weakness of this pi bond, the bond is easily broken and alkanes are more reactive than alkanes. Compounds that can exhibit isomerism are compounds that have different substituents on the carbons connected by double bond. So all terminal alkanes cannot exhibit isomerism. Symmetrical alkanes cannot also exhibit isomerism. Cycloalkanes can also exhibit isomerism. In cycloalkanes, the trans and the cis isomer, just like normal alkanes, trans isomers are more stable than cis isomers. Physical properties of alkanes. Alkanes exhibit weak van der Waals interaction. So their physical properties are comparable to that of alkanes of comparable molecular weight. Meaning that if I want to compare propene, I have to compare with propane. I cannot compare propene with butane. Alkanes have low melting point and boiling point than alkanes. It means that the melting points are lower in alkanes than in alkanes. Melting point and boiling point in alkanes, just like alkanes, increases with increase in surface area, which is increases with increase in carbon, which relates to increase in surface area. Alkenes are soluble in organic solvents and they are not soluble in water because they are non-polar. The S character of alkenes are higher than that of alkanes. This makes alkanes slightly more polar than alkanes. Looking at the structure, alkanes which have sp3 hybridization are going to have more electron density, so they are going to then donate electron to carbon of sp2, which is carbon of alkane. And carbon of alkane are more electronegative because of their higher S character. In this case, the sp2 are more polar than sp3 carbon, meaning that alkanes are slightly more polar than alkanes. Instability of alkenes. The more substituted an alkene is, the more stable it becomes. This is simple because when you have a bench and there are more load on one part of that bench, the bench is going to tilt, meaning instability. So in the same way, when when weights are balanced by the size of this bench, it becomes stable. So that's why substituted are more stable, while non-substituted are least stable, as shown on the slide. In terms of polarity, Cs are more polar than trans, meaning that the boiling point of Cs are higher than that of trans, because the substituents are on the same side of this compound, which causes dipole reinforcement on each other, and hence increasing the net dipole. While in trans, the substituents are adjacent or opposite, thereby cancelling each other and having no net dipole, which is the reason why Cs has higher boiling point than trans. Nomenclature. In naming of alkanes, it is important to consider the double bond when naming. When alkane are being named, first is to consider the longest continuous carbon chain that covers the double bond. So anything that does not fall in that longest continuous chain becomes a substituent. After which you name these substituents alphabetically, irrespective of their position on the longest continuous carbon chain. The example we have on the screen, the longest continuous carbon chain is hex, that is 6 carbon. And on position 235, we have methyl. And for me to name this compound, I will follow the routes that will give this double bond the minimal number. If I follow my right, it's going to be number 4. If I follow my left, it's going to be number 2. So I come from my left. The compound name is 2, 3, 5 hyphen, because number and number is separated by comma. Number and letter is separated by hyphen. Then hex 2-ene or 2-hexane. Talking about the position of this double bond is 2. So this is how to name your alkanes. If it is alkane, because alkane does not have double bond, if I want to name alkane, I have to follow the route that will give the sum of the substituents the minimal number. So I have to follow right or left, any of the routes that will give me the sum of the substituents the lower number. That should be the route I will go with, because there is no functional group to consider in alkane. In this example, the longest continuous carbon chain is 7. It cannot be 8 because when I use the second column where the longest continuous carbon chain is 8, the double bond is not covered. That is why it is termed incorrect. So the longest continuous carbon chain is 7, and I have to follow my left because it's going to give the double bond number 1. Hence, the substituent in this compound is only one substituent, which is ethyl, meaning that this compound is 2-ethyl 1-heptane or 2-ethyl hept 1-ene. In naming cyclo compounds, I have to follow the routes that will protect the double bond as well as the substituent. So 1-methyl cyclopentane, because my double bond is on carbon number 1 and my substituent on carbon number 1. 3-methyl cycloheptane. So I'm going to follow clockwise to make sure that my methyl is having minimal number. In naming a compound, assigning its geometric isomerism, the first step is to use your pencil to divide this compound into half, starting from the point of connection of double bond. Then look at the substituent on the 2 carbons that is connected via double bond. Looking at the example on the screen, the first carbon have hydrogen and methyl. The second carbon have methyl and ethyl. So under first carbon, the priority compound is the one that have higher atomic number. So in this case, methyl is a priority In the second carbon, ethyl is the priority, meaning that this compound is in trans isomer. Now, after considering the geometric isomerism, I will then name. Remember, in naming, just like we said in previous slide, you're going to give the double bond priority, giving it the least number on continuous carbon chain. So I'm going to name and give my methyl carbon number 2, and the compound is pent. So I have pent 2 in. So in that pent 2, carbon number 3 is bearing the substituent called methyl. Then in naming, I say E because it is on opposite sides, which is trans isomer. Bracket. Remember, letter and number will be hyphen. And another hyphen, methyl, E bracket 3, methyl 2 pentene or pent 2 in. The next structure, these priority compounds or substituents are being rearranged in the same side of this compound, meaning they are in cis configuration. So when I want to name, it's still the same compound. Difference is I'm going to put Z to indicate that the compound are in cis configuration. These alkenes are interesting because they are useful in our day-to-day activities. We have it as polyethylene. When this ethylene undergo polymerization, will form polyethylene. These polyethylene are what we call polythene bags. They are also useful as in preparation of polyvinyl chloride, we call it PVC, which are used in pipes and films in production. They are also useful in preparation of ethylene glycol, which is antifreeze agent, and others as shown on the screen, meaning that the alkanes you are studying are not useless. They are very useful, especially in the industry. In nature, alkanes are also very important. Just like whenever you're eating your carrots, you remember that orange pigment in carrots indicates the presence of beta-carotene. We have alkane in lemon, that is the fragrance you normally hear in lemon, which is limonene. We also have double bond on the skin of apple. So meaning that alkane are also very useful in nature because they are very healthy. Why? Whenever you take oil and oil is hard, it means they are saturated. But when oil are unsaturated, it means that they have double bond. Fatty acid in the oil are not saturated. They have double bond in them. That is why they are very healthy for us. Alkanes are prepared from alkyl halide and alcohol via elimination reaction. Remember, by elimination, you're removing something. When we are going to talk about the reactions of alkane, you'll understand that alkane can undergo addition reaction of hydrogen halide to form alkyl halide. So reversible is the case here. So when alkyl halide, in the presence of strong base, which can be sodium ethoxide or potassium tertiary pentoxide, in that case, we are going to form an alkane. Another elimination method that gives alkane is dehydration of alcohol. When alcohol is dehydrated in the presence of sulfuric acid at 170 degrees centigrade, we are going to form alkane. This method is very useful because the subsequent slide we are going to see that when alkane is hydrated, we are going to form alcohol. Just like that of alkyl halide, it is also a reversible reaction. This elimination reaction is stereoselective and radioselective, which made it that the most stable alkane is usually formed as a major product. So when a reaction occurs, elimination reaction occurs, the major product is the one that is isolable, is one you can see. The one that is not stable will not be seen because it's going to destabilize and form series of products that you cannot isolate. So with alkyl halide, under elimination method, the major product is the one that is isolable. When alcohol is dehydrated, the major product is trans isomer. Cis is not stable and cannot be isolated. Remember, in the previous slide, we talked about that trans are more stable than cis isomers. Reactions of alkanes. Because of the presence of double bond, which is weak bond, alkane can undergo addition reaction. Addition because there is space. In this reaction, pi bond will be broken and sigma bond will be left, which means that whenever you're doing addition reaction on alkane, you're going to move from unsaturated alkane to saturated alkane. In this addition reaction, add this reagent either in syn addition or anti-addition. When added in syn, you're going to form cis isomer, and when added in anti, you're going to form trans isomer. Most importantly, the anti is more stable than the syn. Typical example of addition reaction is hydrogenation reaction. Hydrogenation reaction is addition of hydrogen and is a reductive reaction. In that case, a catalyst is needed, which can be either nickel, platinum, or palladium. In this case, you're moving from unsaturated alkane to saturated alkane. This hydrogenation method is employed in production of margarine in the industry, where your oil is going to be hydrogenated under this catalyst to form margarine, which is fats. Summary of addition reactions of alkane. In this example, cyclohexane is being used. The same thing can also happen to straight chain alkanes. The first reaction is hydrohalogenation, where we are adding hydrogen halide. Hydrogen and halogen is added across the double bond. Second is hydration. In hydration, you're adding water. Sulfuric acid is a catalyst. So when water is going to dissociate, it's going to form hydrogen ion and hydroxyl ion. These are going to be added across the double bond. The next reaction is halogenation. In halogenation, halogens are added across the double bond. In halohydrin reaction, halogen and water are the reagent. So at the end, we are going to add halogen and hydroxy group across the double bond. While in hydroboration, which is an oxidative reaction, we are going to form an alcohol. Hydrohalogenation, which is electrophilic addition of hydrogen halide. Like said in previous slide, they are going to be added across the double bond. In this case, hydrogen is a carbocation and halide is carbanion. So when the bond is broken, the bond is going to also break in carbocation and carbanion version. So unlike will attract, forming alkyl halide. This is a typical example of hydrohalogenation reaction. In that, this is a symmetrical alkane, so hydrogen and bromine can be added however I want it. When the alkane is unsymmetrical or asymmetrical, it means that they cannot be divided into two equal halves. Then Markovnikov's rule will be employed. In this Markovnikov rules, we simply add hydrogen to the carbon connected by double bond that have more hydrogen. So carbon that have less hydrogen will be given the halogen. In the example of propene, carbon 1 has 2 hydrogen, while carbon 2 have 1 hydrogen. So Markovnikov said that we're going to give hydrogen of this HCl to carbon 1, while carbon 2 that have just 1 hydrogen will be given chlorine, forming the product of 2-chloropropane. Example of Markovnikov's rule. So whenever you see a reaction of alkane and reacting with hydrogen halide, whether HCl, HBr, or hydrogen iodide, what you look at is this compound symmetrical? by how do I know if it's symmetrical? Can I divide them into two equal halves? If I can, Markov-Nikov's rule is not important. If I cannot, Markov-Nikov's rule is essential in forming the product. So the first compound, the compound is asymmetrical because the first carbon have two, second carbon have one hydrogen. So following Markov-Nikov's rule, I'm going to give hydrogen to the first carbon and chlorine to the second carbon. Looking at the second compound, this compound is internal alkene, meaning the double bond is in the middle of the compound. Then the first carbon we are looking at carbon number, the carbon that connects the double bond. The first one does not have hydrogen, it has methyl, while the second one has hydrogen. So hydrogen is going to be given to the second one, while the first one is going to give in the halide, which is bromine. The last carbon is symmetrical, meaning they can be divided into two equal halves. So I can give my hydrogen to the first carbon. I can also give my hydrogen to the second carbon. However I do that is still the same. In a reaction where you are having hydrogen halide and peroxide is added, it means that this compound or this reaction is going to undergo anti-Markov-Nikov's orientation. In that sense, the carbon that have more hydrogen will be given halide. The carbon that have less hydrogen will be given hydrogen. So, whenever you see a reaction of alkane with hydrogen halide, whether bromide, chloride, or iodide, what you're going to look at, if there is peroxide, is going to be anti-Markov-Nikov's orientation. But if there is no peroxide, go ahead and employ Markov-Nikov's orientation only on asymmetrical alkene. Hydration reaction is addition of water to alkane to form alcohol. In this hydration reaction, sulfuric acid is used as catalyst, just like we said in the beginning of electrophilic addition reaction of alkane. The water is going to dissociate into hydrogen and hydroxyl, and the same thing will happen to alkene. So unlike will attract to form alcohol. Remember, the hydration of this alcohol is what gave alkene. Alkene can also react with alcohol using sulfuric acid as a catalyst to form an ether. In this reaction, alcohol can also react with alkene to form an ether. This reaction, depending on the nature of the alkane, can also undergo Markov-Nikov's rule because the alkane on the equation is asymmetrical. Markov-Nikov's rule can play. In that Markov-Nikov's rule, we are going to give the terminal carbon hydrogen, and we're going to give the second carbon the methoxy, forming the ether. But if the compound is symmetrical, we can give hydrogen to any of the carbon and we can still form the ether. When halogens are added to alkane, vicinal dihalide are formed. In halohydrin formation, alkane will react with halogen and water. They are going to form a compound that has both halogen and hydroxyl as their substituents, which are called halohydrin. If the halogen is chlorine, we call chlorohydrin. If the halogen is bromo, we call it bromohydrin. Hydroboration is an oxidative reaction and is a two-step reaction that converts alkane to alcohol. The first stage is addition of borane. When borane is added, we are going to form alkyl borane. An oxidation of this alkyl borane will form alcohol. This is a typical example of hydroboration. So if you're in an exam and you see BH3 with peroxide and hydroxyl, you know that this is hydroboration reaction. So the product you should be looking at is alcohol. Another reaction that alkanes undergo are oxidation reaction. This oxidation reaction can be without cleavage or with cleavage. Oxidation without cleavage, first is hydroxylation of alkane with permanganate. So when you see a reaction of alkene and cold alkaline solution of permanganate is added as a reaction, the product you're going to obtain from this reaction is diol. It means that across this double bond, the carbon that is connected by double bond, both of this carbon is going to have hydroxy group because it is called alkaline permanganate. This is a method used in identification of the presence of unsaturation in the lab, where the purple color of permanganate will be changed to brown. You know that the compound involved is an unsaturated compound. Remember, unsaturated compound is compound that have double bond. It can be double bond, it can also be triple bond. Under oxidation without cleavage, we have epoxidation. In epoxidation, we are going to use peroxybenzoic acid to form an epoxide. So whenever you see a reaction of alkene with peroxybenzoic acid, the product you're going to form is epoxide. So number of carbon in the alkene is going to determine the number of carbon in epoxide. Next is oxidation with cleavage. The first one is ozonolysis. In ozonolysis, we are going to add ozone in the presence of zinc and water to form ketone. So whenever you're talking about ozonolysis, what you're going to form is ketone or aldehyde. Now looking at the reaction, remember there will be a cleavage on the double bond. When this compound is cleaved, it's divided into two. The right section of this compound does not have hydrogen, so it's going to form a ketone, while the left side have hydrogen, is going to form an aldehyde. So under ozonolysis is an oxidative reaction whereby the bond in alkene is cleaved into two. Depending on the nature of the carbon that connects to this double bond, we can form either aldehyde or ketone. So in example, when you see alkene reacting with oxone, that is O3, then there will be, and there is zinc and water, you know is ozonolysis. Then what we need to look at is this alkane. What is the nature of the alkane? The carbon that connected the two carbon connected by double bond, what is the nature of this carbon? Do they have hydrogen? If they have hydrogen, under ozonolysis, you're going to form an aldehyde. Simply put oxygen in the presence of that hydrogen. Then if they don't have hydrogen, also put oxygen, making it a ketone. So we have aldehyde and ketone in this particular compound. But if it's symmetrical alkene, I'm going to end up having two aldehyde. But as long as it's asymmetrical, it can be aldehyde or ketone. It can also be two ketone, depending on the nature of the alkene. But when this oxidation is using permanganate with heat, at times they can put acidified. It means that the reaction is very vigorous. Terminal carbon is going to form CO2, while a carbon that have hydrogen is going to form carboxylic acid. Those that have no hydrogen is going to form a ketone, just like what happened in ozonolysis. Typical example of oxidation with cleavage in alkene. The first compound is pent-1-ene because the double bond is on the terminal carbon. That terminal carbon is going to form CO2. So because the second carbon have hydrogen, is going to form carboxylic acid. Remember, it's vigorous oxidation. In ozonolysis, it's an oxidation but not vigorous. That's why the aldehyde form cannot undergo further oxidation to carboxylic acid. But because this is permanganate, whenever an aldehyde is formed in permanganate, there's a tendency that the reaction doesn't stop until carboxylic acid is formed. So because this is permanganate, that's why we are having carboxylic acid. But remember, in ozonolysis, we still have the same thing. But because it's ozonolysis, we cannot further to carboxylic acid. It ends in aldehyde. In second compound, we can see that this compound is not symmetrical because the carbon connecting to double bond, one have methyl and one have hydrogen. The one that have methyl is going to form a ketone. The one that have hydrogen is going to form aldehyde, which further oxidizes to carboxylic acid. That is why what we're going to see is carboxylic acid. The last one is very symmetrical alkane. Because they're symmetrical, they're going to form aldehyde and further carboxylic acid. That's why we are putting 2, because they are similar. So they're going to form 2 acid. Either you see hot, you see heat, or you see acidified. They are all talking about vigorous oxidation under alkane. Polymerization is a process whereby small molecules, which are monomers. Polymerization is a process whereby small molecules or simple molecules, which are monomers, join together to form a larger molecule called polymers. In alkanes, polymerization is influenced by acidic catalysts and high temperature and pressure, and they're going to give up to 100,000 of monomers per molecule. Example is ethylene. Under polymerization is going to form polyethylene. So this polyethylene can go as far as hundreds of thousands of the original unit. It means that hundreds of thousands of ethylene can be used in forming a polymer called polyethylene. That's why we have low density and high density polyethylene. There are 2 types of polymerization. We have addition polymerization, which is seen in ethylene forming polyethylene. We also have condensation polymerization, where monomers come together to form a polymer by eliminating water. These are common addition polymers. We talk about polyethylene. Like I said in the previous slide, they can have low density and high density. Remember, hundreds of thousands of this ethylene can form polyethylene. We also have PVC and others as shown. We've come to the end of this class on alkene. Remember, alkene are unsaturated compound and sp2 hybridized, trigonal planar and bond angle of 120. Because of the pi bond is weak, that's why it undergoes reaction more than alkane. Till I see you in the next class, where we'll be discussing and talking about alkyne. I wish you success in FSC 112 exams. Thank you.